Hello, Professor Sargent here with you again. Before I launch into the examples, I want to remind you that a continuous random variable, the way some authors refer to that, is that it's a random variable where you cannot count. The way I put it is there is no smallest distance between two different scores. Our main focus is going to be on normal distributions. However, another type of continuous random variable is a uniform random variable. And the graph of a uniform density function would be looking like a rectangle, uniform because of horizontal. Okay, so suppose along an 8-mile bike path, the probability of an accident along the path follows a uniform density distribution. Because the total area between your curve and the horizontal axis has to be 1, then what we're going to have, since this is 8 miles long, is a height of 0.125. So to graph the density function, we're going to have a rectangle, and that rectangle is going to be 0.125 units high. In case I didn't show that. Okay, let's see, I did show that, I guess. 1 divided by 8 is 0.125. So here's our graph. And we are asked first, what is the probability of an accident in the first 3 miles? I'm going to make this a little more than is needed, but I want to compare to when we have a finite sample space where the outcomes are equally likely. We took the size of the samples, the size of the event over the size of the sample space. So similarly, we're going to compare the area of the event to the entire area. And again, the entire area between a density curve for any random variable, the total area between that and the horizontal axis is going to be 1. And then we would have a height of 0.125 times the base, which is 3. And that's going to give us 0.125 times 3, or 0.375. Now, a much easier way to do that would have been to say, all right, we've got 3 between here and 0 over 8. 3 over 8 equals 0.375. And let me do one more thing here real quick, if I can. There we go. It would be a good idea to shade the region where you're looking for the probability of it. So we're seeing that this is 3/8 of the entire area, or 0.375. Now, in part B, we're looking for the probability of an accident in the last 5 miles. Well, that's the complementary event of what I've shaded here. And so you could say that's been shaded in white. Therefore, our probability is going to be 1 minus the 0.375. And that is going to equal, relax, kitty cat. Oh, let's see here. I believe 0.675. That was incorrect. It is supposed to be 0.625, which makes sense because we could have also done 5 miles times 0.125 from the height, and that would get us 0.625 as well. All right, let's see here. What next? It's the probability of an accident between miles 2 and 7. Well, let's first get rid of that shape. That's also a 5-mile stretch, but I'm going to do the shading anyway. From miles 2 to 7. Talking about the probability of an accident happening in there. That's a 5-mile stretch as well. And 5 times 0.125 is 0.625. So there's that. Let's see here real quick. Just make that look sort of kind of pretty. Didn't work. But in the meantime, while I'm trying to do that, the last part of this question, you're at the start of the bike path. There's a 25% chance of an accident within how many miles? We're working backwards. And so what you could do is convert that to a decimal and multiply 0.25 by 8. In other words, that's 1/4 of 8. So that should be 2 miles. And if I check that by shading from 0 to 2, then we should see that we have 2/8, which reduces to 1/4. That's equal to 25%. So our area of that shaded region is 2/8, 0.25, 25%. Now it's on to normal distributions.